Programmers spend a lot of time debugging software. That is, trying to understand why a program doesn't behave as intended. If you are a programmer, you probably have fun memories of days spent chasing an elusive bug in your program. Spark is a language plus tools which helps you by making sure a program behaves as intended. First, by making sure there are no memory errors, concurrency errors, or any other kind of runtime error. Then, by allowing you to write down intended properties of the program as contracts and making sure the program respects these contracts. The net result is a much stronger assurance that the program behaves properly than what you can achieve with traditional verification means, including testing, fuzzing, static analysis, and reviews. Here's a program in Spark. It takes a natural number, extracts its ones digit and tens digit, does some strange computation, and updates its argument. This program is in fact in multiple languages. This procedure is in Spark, but its caller is in C, and the main program is in Ada, the base language for Spark. This is possible thanks to the facilities in Ada for importing from and exporting to other languages. Here we say that procedure passed to C is imported from C with the same name, which allows us to call it in the Ada code. We can compile and run this code. We have checked that when the argument is 42, the result of the computation is 42. But what about other values? Here we can specify using a contract that for special values 0, 21, 42, 63, and 84, the computation returns its argument unmodified. For all other natural numbers, the argument is modified. Using the Spark menu, we can ask the tool to prove that the program respects this contract. If we forgot one of the special values, say 42 here, and we will run the tool, it warns us that the contract is not proved, and it even gives us the missing value here, 42. If the safety or security of your system depends upon giving the right result for this computation, what are the odds that testing or fuzzing or static analysis or review will catch a mistake that only affects a few input values? That depends on many factors. The benefits of formal program verification with Spark is that it will catch it always. You can adopt Spark progressively in an existing codebase in Ada, C or C++, and raise the level of assurance of your Spark code as time goes by, from adherence to the Spark subsets, what we call the stone level, up to correct data flows, the bronze level, absence of runtime errors, the silver level, verification of program properties expressed as contracts, the gold level, and even full functional correctness where appropriate, the platinum level. You can save time and efforts by getting strong guarantees that the program behaves appropriately, which also means that you can focus your time and efforts on other properties that are not easily expressible or verifiable automatically. Spark 21 supports many new features introduced by the upcoming standard Ada 22X. In this function release, I'm using a declare expression, which allows to declare constants inside an expression. And for the second constant update here, I'm using a delta aggregate, which replaces update attribute, previously known in Spark, to update string base at index 8 with value 1. Inside the body, in the assignment here, I'm using the symbol @ to refer to the variable being assigned, which avoid repeating previous here, computing the same string 21 as above. Spark can readily prove this subprogram correct. Spark 21 also supports access to subprogram with contracts. Here, in this type, I'm adding a postcondition which says in particular that the year, being the two last characters extracted from the string, is equal to 21. Using an iterative component association here, that is, for each index j in the array, I'm giving the right character based on its ASCII number here. And finally, I'm assigning to this next variable of pointer type an access to the previously seen function release. There is a check that the postcondition and precondition match here. That is, the precondition of release should be weaker and the postcondition of release should be stronger. And this is checked by Spark. After the addition of pointer support in Spark 20 based on ownership, Spark 21 has the detection of memory leaks related to pointer usage. Let's see an example. Here, x and y are dynamically allocated. Then variable z takes the ownership of the memory pointed to by y. Then z.all is reassigned to the value of x. There is a possible memory leak here, that is, the memory pointed to by y is leaked. Afterward, x is reassigned, but never freed. There is another memory leak here at the end of the scope of x, which is reported on the declaration of x. Finally, z is freed, but not the underlying memory, so there's a memory leak reported here. Let's see. All three memory leaks are detected by Spark. Until now, Spark always required to manipulate partially initialized data within the boundary of a subprogram. With Spark 21, it's now possible to declare that an object or type has relaxed initialization with this aspect, which then allows to manipulate the object freely with respect to initialization. The user has to specify what content is initialized. For example, here, the contents array in the stack is initialized up to index top at all moments. Spark checks that the push and pop API of the stack respect this predicate. That allows to declare a stack here without to initialize it fully and manipulate it correctly. Let's see. Spark checks that there are no problems here. If we remove the specification of partial initialization and reanalyze the client code, Spark now reports that S is manipulated without being initialized. Spark 21 supports the units big integers and big reals from the new standard, which goes beyond the previous support for overflow modes. This is practical in particular for stating arbitrary lemmas about arithmetic without having to worry about overflows. Here in this lemma add mult, we prove that multiplication is distributive over addition, so x plus y times z is equal to x times z plus y times z. This is proven automatically, so there is no body in this lemma procedure here. This is proven by Spark. As with every release of Spark, we have worked on improving the messages from the tool. Let's see an example. We have here a procedure inc that increments its input and states in postcondition that x is equal to add 1 applied to the previous value of x with the obvious supplementation. Spark reports first that there is a possible overflow in the implementation. Like previously, it gives a possible counterexample value, as well as now a reason for the check, the fact that the result of an addition must fit here in a 32-bit machine integer. It even suggests a possible fix that the subprogram here should have a precondition. The postcondition of inc can be proven either. We have here a possible counterexample and now a possible fix that the function add1, which is called in this postcondition, should have itself a postcondition or should be an expression function. Otherwise, the prover cannot know what add1 means. That same information is available also on the command line. So if we run getAddProof from the command line, the error messages here include all the information previously displayed in GetStudio. We have already started the work towards the next release of Spark along three main axes. First, we will continue on our successful track to integrate automatic provers in Spark, which started in 2014 with AdaCore, followed by CVC4 and Z3, and later the CodePeer static analyzer. Spark 22 will include the constraint solver Colibri, which will help with proving nonlinear arithmetic properties and properties that mix integer and real arithmetic. We will also continue improving interactions with the tool, with a special focus on counterexamples. These were added to Spark 16 and have been greatly improved since then to offer a better display of counterexamples, a better choice among candidate counterexamples, and a better generation of candidates. Spark 22 will include automatic checking of counterexamples by symbolic execution in order to first discard infeasible counterexamples and then issue useful recommendations for a fix. Finally, we plan to support a larger language subset, in particular when it comes to pointer support, which started with dynamically allocated data in Spark 20 and was extended to callbacks in Spark 21. We're looking at supporting other types of pointers in Spark 22, subject to suitable restrictions. If you are interested in that topic, you are invited to follow the discussions that will take place on our dedicated GitHub project for the evolution of Ada in Spark. For more information about AdaCore and its products, speak with sales@adacore.com, read our recent articles on blog.adacore.com, ask questions on Gnat Tracker if you're a customer, and visit us at www.adacore.com.